So, hello again, and today we are going to conclude our part of binary shift keying signal demodulation. We already have discussed optimum correlator receiver. Optimum correlator. That was our last time. And today we are going to discuss the second approach, how we can perform the best possible detection of signal in noise by using matched filtering. So first I'm going, of course, to tell you a little bit more about what is filtering. I presume that you should have already learned something about filtering, so I will maybe somewhere repeat, but I will be very brief and will not delve into details, since filtering is a big course itself, and well, we are just going to need some specific type of the filter for our task, which basically is the same thing as the correlator. So let us start by talking about filters. What are filters? What kinds of filters are there? And which one are we going to use for our task at hand? So basically, a filter is the signal processing component, which forms the output signal with some desirable for us properties. So most often we are talking about filtering as a frequency selective processing, meaning that, for example, we have multiple times discussed that we have several channels, for example, channel 1 and channel 2 and so on, and we need somehow to separate those channels. For that purpose, we can use some bandpass filter and keeps only our signal. That removes some noise as well, and so on. So this is a so-called frequency selective filtering. There are also other types of filters, and there are more than 2 types, but we will be interested the most in the matched filters today. Those are used to perform a search of some specific pattern in our signal. So consider that we have some noisy signal, and we need to find in that signal this part, right? So we are going to design a special filter which is made to look for some specific pattern in our signal, and when they match, the filter will generate the high value of energy. So this is basically exactly what we need to perform the receiving of the signals in case of noise. So we will talk mostly about matched filters today. And for any kind, be that frequency selective filtering or matched filtering, the output signal depends on input signal, of course, and the properties of the filter, which are usually specified in form of the impulse response. Impulse response. We will talk right now what is that if you don't remember, but the idea is quite simple. So the output signal is calculated according to this mathematical formula from input signal and filter impulse response. Please note that here we have some time moment t for which we are calculating the output signal value, and we integrate over some other variable tau, yes, which is these integrals variable of integration. And well, basically what we can see here is that this impulse response is mirrored in time. So basically, if our original signal was this, then after this mirroring operation, it will become like this, right? So it's flipped, and it's very important. That's actually what changes this formula from other formula of correlation, which we calculated previously. We will talk about correlation, and this is called convolution more later today. Convolution, right? But basically, filter calculates the convolution between input signal and filter impulse response. So that's how filter is operating, and that's how we model it in our computer software. So what are the properties of the filter which describe how it will process our signal? Basically, most often we are interested in two properties of the filter. The first one is in time domain, and that's impulse response. And the second one is in frequency domain, and that's the frequency response. So naturally, these two can be calculated one from another by using Fourier transform. So, for example, if you happen to know the impulse response, then by applying Fourier transform to it, you can calculate the frequency response. If, however, you have some desired frequency response, for example, you are prototyping some kind of the filter and desire to create a filter with such frequency response, let's say, for example, right? So in this case, you can find what impulse response it will have by calculating inverse Fourier transform from this frequency response, and then you will get a time function, which is impulse response. So they are interconnected and form a unique pair. So what is the impulse response? The impulse response, as it's coming from its name, is the reaction of the filter when we send to the input an impulse. So consider that our filter is some kind of the black box with unknown properties. We don't know what is this filter doing. So we are going to find out that by sending a probe impulse at the input, single impulse, and listening to the output. So the output will have generated some impulse response. So that's very similar to some kind of, I don't know, bell, which you can hit, and then you hear how it sounds, right? So that hit is the impulse, and that echo sound is the impulse response. So this is generally a universal term, so it's not only applied to filter, but to any systems, including social systems, right? You can also have some impulses sent to the social communities or something like that. And well, we can then observe how the social is reacting to some impulses, let's just say so. Yes, so basically this comes to any kind of the system, which happens to be one of the systems filters of which we are talking today. So if we send to the input some delta function, which is mathematical abstraction, and sorry if you hear that, that's my dog, and that is mathematical abstraction with infinitely large impulse amplitude and infinitely short duration. So it's close to zero. But basically, in practice, we are going to use some sample with amplitude 1. Right? So we send amplitude 1 and the next values are zeros. That's how we calculate impulse response for some digital filters or analog filters, for example, right? So And yes, as I have said, we have digital filters, we have analog filters. And depending on the length of this impulse response, these filters can have infinite impulse response, and they are therefore called infinite impulse response filters. And they can have EER, and they can have finite impulse response FIR, right? So in case of the finite impulse response, this impulse response has some fixed duration, for example, 100 samples, and afterwards this gives zeros. For infinite impulse response, this impulse response is infinite. It's close to zero, but it never reaches zero. So it's said that it is asymptotically close to zero at the infinity, right? So most of the analog filters, well, in fact, all analog filters are infinite impulse response filters. And it's impossible to design finite impulse response filter in analog form. So finite impulse response filters can be only digital, right? And well, infinite impulse response can be both analog and digital. We will talk, of course, more of the digital filters for our simulation today on our practical exercise, because we are going to use MATLAB. I'm Octa, the same. And well, we happen to work with digital data in that software, right? So that's an impulse response. Now, frequency response, we already have covered this topic previously when we talked about channels, for example, right? That we need certain conditions for this frequency response of a channel in order for that channel to not distort our data. And we know that this frequency response is most often given in complex form, consisting of absolute value, modulus, and argument. So that's why we always present the frequency response in form of two plots. The first one is amplitude frequency response, and the second one is the phase frequency response. That is universal again for any kind of the filter. And the example for fading channel from our previous lecture, one of previous lectures, was this picture when we had direct radio wave and some reflected and diffracted radio wave distorting the amplitude frequency response of the channel. So ideally, our frequency response of the channel must be somewhat more or less constant in our frequency band where we are going to transmit the signal. So this is our frequency band, which affects our data transmission rate, as we have already discussed that during our discussion of the Shannon theorem, information theory, and so on. And well, we need more or less constant signal level in this band. Now, because of some distortions in channel, this can be, well, not true. So that's meaning that channel can actually be considered to be a filter too. Well, that's a model of a channel. So another common topic is the filter transfer function. Transfer function is basically a transform of the frequency response. For analog filters, it's Laplace transform, and for digital filters, it's Z transform. In both cases, this transfer function is written as a division of two polynomials, right? So we have polynomial in numerator with some coefficients b, and polynomial with coefficients a in denominator. And it's the same for binary. Not binary, I mean digital filters. The only thing that is different is this variable its Laplace transform operator and its Z transform operator. And well, most often the task of filter design is reduced to finding these coefficients. So we have these coefficients, then we have a filter with desired properties. So, for example, we have some properties like what cutoff frequency do we need, F0, right? What level of the signal we must provide at some control frequency, and what's the minimum allowed value in the passband, so that would be H minimum for our filter. So given these conditions, we then use different methods to calculate what filter order do we need and the coefficients of the numerator and the denominator of the transfer function. And when we calculate that, we have the filter calculated, which can be then implemented and used, and it will have this amplitude frequency response as is requested. So that's in general about filters. Now let us talk more about what exactly is matched filter and why do we need it and how it can help us to receive signal in noise. So the idea of the matched filter is, as I have said, to make a search for some specific pattern in a signal. And even more, the signal itself can be noisy. As you can see in this picture, we have some noisy signal and we have a hidden pattern in that signal which we need to find. Where exactly is that located? Of course, in order for this to work, we need to know that pattern. Well, in our case, it's okay because we know the carrier signal and we used them in correlation receiver. So just like that, we can use them here as well. So let us see this short video, which is from this link, right? How this search is performed. So we start with our pattern or reference signal fixed here. Then we move it along our received signal, and when they are aligned, the output of the filter will produce the maximum possible value. And then as the signal goes away, the value will decrease again. So let's see how it works. Pause the video when they are aligned. So you can see that signal moves. Some values are calculated for output. Now we are getting close to our signal. And now they match completely, right? So then that's when we have calculated the maximum value at the output of the filter. Now, as this signal will continue moving around, right, the value will continue to decrease. And then, well, we have exact location when our pattern signal has been observed in this received signal, right? So if we look closer here, you can see that actually this maximum matches directly the beginning of this pattern. Now we know this pattern form, so we know where exactly that signal is hidden. And well, you can consider that we actually have received that signal without noise. We have found where it's hidden, right? So that's how matched filtering works. So the only question is, how do we put in this desired pattern into the filter? So we have some filter, right? And we send to the input of the filter this noisy signal. So that's signal with noise. And we hope to get some information at the output. Where is our pattern hidden? So that's would be some output signal y of t. But we also need somehow to put inside that pattern. how do we do that? Well, as we have discussed, the only thing that determines output signal for a filter are input signal, which is not in our control because we have to process whatever signal we have received, and the impulse response, which we can change as we need. So basically, that's where we are going to put our pattern into this impulse response. So we need to create some special impulse response for the filter in order for this to work. And that's the answer to the question, right? So the filter impulse response need to contain this pattern in itself. So let's see this example. We have some input signal, we have some pattern or target signal, which we need to find in this input signal, right? So we can see with our eyes that this pattern is located here, right? And well, we have some output signal which must show us the maximum value at the moment when this pattern or target signal will be aligned in time with this input signal, right? And that's, well, how this filter works. So how do we specify this impulse response and how do we put this target signal into that impulse response? Well, basically, the answer is already hidden in the formula. Remember how I told you that we need to calculate the mirror of the signal for the convolution? Well, actually, because of that, we need this impulse response to be exactly our signal in mirrored form. So, and these two formulas are given for analog case and for digital case. So as you know, for digital case, this integration is replaced with some finite sum consisting of L members, which we need to sum up together. In integral form, its number of added elements is infinite, right? But for finite sum, we have only some limited number of these samples, right? And basically, in fact, this is close to the order of the filter, especially if we are talking about finite impulse response filters, which we are going to use in our practical exercise today. And well, other than that, these formulas are no different. We multiply signal with impulse response and then we add up that together. So we need to flip time for our impulse response, and therefore the signal which we are going to search for in our received signal needs to define this impulse response. So yet again, you can see here that the impulse response for some pattern which we desire to find must be actually the very same pattern signal, only reversed in time, meaning that it also must be mirrored. So basically, then we will have double mirroring. So first time we mirror the signal and create the impulse response, and the second time we are going to mirror this impulse response during the calculation of the convolution. And that's how we actually are going to get the formula of correlation, which we already discussed at our last lesson last week. And well, you will see for your own eyes now that basically matched filtering and correlation receiver calculate the very same thing. And therefore, of course, they are equally effective in their optimality. So, for example, consider that we have some pattern signal represented by 8-bit ASCII code word like this. In order to be able to find this pattern in our received noisy signal, right, we need to create a matched filter with impulse response, which is a reverted code word, right? So here you can see 1, 0, 0, 1, 0, 0, 1, 1. And that's exactly the reverse of the impulse response. So the impulse response is quite easy to calculate. We just take signal which we need to find and read it from the opposite direction. So we flip it horizontally, right? And well, that's quite easy to do in simulations, in theory, but of course that's some problems when we try to make practically such filters, especially considering that we are using high frequencies and we need analog filters. As I have already told you, we cannot really create precise analog filter with this impulse response because analog filters have infinite impulse response, and here we have specified how long this impulse response must be. So, well, this is basically more often used in simulations and studies than in practical schematics. In practical schematics, we are using correlation receiver, which is just as good from the error probability perspective as matched filtering. So now let's talk about relation between correlation and convolution. Basically, let's write down both of the formulas in terms of our optimum receiver. When we have received signal u of t, unknown exactly which it is, yeah, so it's received, which can be for binary case either S1 representing signal 1, either S2 representing signal 0, right? So only one of these two signals could have been hidden in noise in this received signal. We don't really know which one, and that's the task for our receiver to determine, right? So we are doing that by calculating correlation integrals, by multiplying with each of these two signals. So we try this correlation integral for S1, and the second correlation integral we calculate for S2, right? And this is the formula for correlation integral from 0 to some symbol duration, multiplication of these two signals, and that's value after the complete integration. Now, as we know, matched filter calculates convolution. So this is correlation, and this is convolution. And the formulas look different, right? At least for now. They, of course, resemble each other because, well, we have in both cases integral with the same duration, we have received signal, we have some other signal which is also multiplied, but, well, they are a little bit different, where impulse response, let me remind you, is actually the mirrored version of the signal pattern which we are looking for. So basically, this is actually our SI signal, right? So if this is the same as SI from tau, then our formulas actually would be really the same. So let's see if we can transform this second formula into this first formula. The first step we are going to do is actually to put and substitute this impulse response signal into this formula. Let's see what happens. So, considering that our H tau is actually SI T symbol mean minus tau, and substituting it instead of HT minus tau, here, we would get this. Now we need to open brackets, and actually, as we have already seen from our practical exercise number 4, when we calculate correlation integral, this correlation integral slowly increases in time and maxes out at the symbol duration. And that's when we are performing the comparison with some threshold. So here we have some threshold, and then here we compare value with the threshold. So the comparison is performed exactly at this time moment. And we are going to substitute this t for this symbol duration. Now integration is calculated over tau, right? So this t is a fixed number, which won't really affect much. So we substitute t for symbol duration. So we get it here and here. Now, after opening these brackets, we can reduce these values. This minus and this minus would give us plus, and we would get the formula of the correlation, right? This is just one number, actually the same energy, and the result would be either energy of the signal if U is equal to Si, or it would be 0 if U is not equal to Si. The very same way as it works for correlation integrals. So hopefully you can see now that correlation and convolution are literally the same thing. The only difference is that convolution has one of the signals mirrored. So basically, if you calculate correlation and you mirror one of the signals, then you get convolution. Now, since we need for our receiver to anyway calculate correlation, then we really have to mirror another signal or the same signal one more time. So basically, for optimum receiver, if we calculate convolution, then we need to mirror the signal, and we do that when we create an impulse response of our desired target signal. Like this. This is the time when we perform the second mirroring. And double mirroring of the same signal, well, actually reverts the signal to original, and we get the correlation formula. So that's the idea and mathematical some kind of proof that actually matched filtering and correlation receiver work the same. We will see, of course, in practical exercise that we get slightly different time diagrams, but the result, nonetheless, will be exactly the same as in our fourth practical exercise. So let's see now how we can put that to work in our receiver with matched filtering. So the idea is quite simple. We have some signal which we send through the channel. There we have some noise added to our signal, and then we need to clear the signal of the noise. And for that, in this particular case, we are going to use a matched filter, which is set to search for the signal with this shape, right? So we are going to find impulse of 1 for this signal. And when they match, they get more or less high energy. Because of the noise, of course, we will not get maximum energy. And when actually we receive a 0, which is represented by negative voltage in this particular case, right, we would get a negative energy. So after detecting this signal, we receive data as it has been sent. Of course, we need to design these matched filters, which again is not a problem for a simulation, but can be a big problem if we are working on some hardware. Because, well, basically in analog form, it's quite problematic. In digital form, which is well, basically simulations, and we can, of course, also work on a digital signal processing. This is not a problem. The problems are with analog filters. So, let's resume how our matched filtering receiver works. So, first of all, we need matched filter for each known signal type. Well, we are not talking about binary amplitude shift keying or phase shift keying, because actually there we can do nice with only one filter. But in general, as for frequency shift keying and other types of modulations, we will need to design filter for each of the known signal type, meaning that if we have, for example, 4 different signals, then we are going to need 4 matched filters for each of these signals. Once again, since we know these signals, it's not a big of a problem to reverse this signal in time, and that would be the impulse response for each filter. Now, we are going to send what we have received to any of these matched filters. So all 4 filters will receive the same noisy signal, but only one signal will produce the highest energy value. So we need to compare the outputs of all of the 4 filters and select the highest value, which again works exactly the same way as it has been working for a correlation receiver. So this structure is actually very similar to correlation receiver, except that in correlation receiver we had these matched filter separated into multiple blocks. So we had generator, we had multiplication, and we had integration, right? So that all can be substituted by this matched filter. Now, consequently, it can be seen that we no longer need to generate these signals. They are put into our filters and are stored there. So we only design these filters once and no longer have to generate these signals at the receiver side. In general, energies of our signals can be different, and that's why we need to center these signals around 0. But if energies of all signals are equal, then we don't need to do this. But in general case, of course, energies can be different, and then we would need this centering. And the decision is performed by comparing all the outputs of these filters and selecting the highest value. So this works exactly like a correlation receiver. Of course, this approach has multiple disadvantages, some shortcomings. The main shortcoming is that it's not always possible to design filters with these impulse responses, especially in analog form. Now that's a problem. Secondly, if we have some channel with distortions, for example, as it has been shown in this picture, right? Then we need to know the frequency response and the impulse response of the channel as well in order to make according changes. So this is also not always possible, can be problematic, especially if we are talking about mobile communications when we have movement and this impulse response actually changes in time. So this can be again problematic. And of course, as I have already multiple times said, we will meet some difficulties if we are trying to implement that in analog form. So this is a brief theoretical introduction to this optimal receiver with matched filtering, and that's all for the lecture. And next lesson today, we're going to make a practical exercise when we are going to calculate these matched filters, right, and get these time diagrams, which are a little bit different than for correlation receiver, but you will see that they actually produce the same signals. So we will continue after a short break at let's say 13:30, we will work on the practical exercise. I have already uploaded that at the authors guidelines for this exercise. And today, afterwards, we'll conclude with work on your course project when we will talk about simulation of the error probability estimation. But for lecture part, that is all. Thank you, and see you in 15 minutes.